Hello! Welcome to today's lesson on understanding the variation in current, potential difference, and resistance in a series circuit. Today, we will firstly introduce series and parallel circuits. We will then investigate how the current behaves in a series circuit. Next, we will understand how voltage is divided among components in a series circuit. Finally, we will learn how to calculate the total resistance in a series circuit. So far, we have explored the basic principles of electricity, including the concepts of current, voltage, and resistance. We have also discussed Ohm's law and its importance in understanding how electrical components interact within a circuit. Building on this foundation, we can now delve deeper into how voltage, current, and resistance specifically behave and interact in a series circuit. Let's get started. In electrical circuits, there are two main types of connections: parallel circuits and series circuits. The key difference between them lies in how the components are connected. In a series circuit, all components are connected end to end in a single path, so the current flows through each component one after the other. On the other hand, in a parallel circuit, components are connected across multiple paths, allowing the current to split and flow through each path separately. We will further examine parallel circuits in our next lesson, but we will be focusing on series circuits for today. In a series circuit, the current is the same through every component because there's only one continuous path for the electrons to flow through. Imagine a single file line of people walking through a narrow hallway. Everyone in the line must move at the same pace because there's no room to overtake or slow down. They're all following one another closely. Now imagine there are checkpoints representing components in the circuit along the hallway. Every person, representing electrons, must pass through each checkpoint one after the other. The number of people passing through each checkpoint per second remains the same because there's only one line and everyone is moving together. This is similar to how the current, which is the flow of charge, remains constant through each component in a series circuit. This also explains why an ammeter, which measures the current, is connected in series with the components. Since the current is the same throughout the entire circuit, the ammeter will accurately measure the current passing through any component in the circuit. Let's solidify this with an example. Imagine you have a series circuit with two components, and you measure the current through the first component as 2 amps. Since the current is the same throughout the entire series circuit, the current through the second component will also be 2 amps. In a series circuit, while the current remains constant throughout, the voltage is divided among the components. Let's go back to our single file line analogy, but this time imagine each person is carrying a certain number of tickets, representing the energy they have. As they pass through checkpoints, which represent the components in the circuit, they have to hand over some of their tickets to the guards at each checkpoint to continue. Some checkpoints might require more tickets than others, depending on how much work needs to be done there. By the time the people reach the end of the hallway, they've handed over all their tickets. They have no energy left. Similarly, in a series circuit, the electrons carry energy supplied by the battery or power source. As these electrons pass through each component, they hand over some of their energy, which causes a drop in voltage across each component. By the time the electrons complete the circuit and return to the power source, they've used up all the energy they were carrying. This ensures the total energy used by the components equals the total energy supplied, maintaining the conservation of energy. So while the current remains the same throughout the series circuit, the voltage, or potential difference, is split across the components, depending on how much energy each component requires. Let's examine a simple circuit. Suppose you have a series circuit with 2 resistors. The total voltage supplied by the battery is 10 volts. If the voltage drop across the first resistor is 4 volts, how much voltage do you think will be dropped across the second resistor? Well, if the electron starts with 10 joules and gives 4 joules to that first resistor, then it must give the remaining 6 joules to the second resistor. Hence, the voltage drop across the second resistor will be the remaining 6 volts. In a series circuit, the total resistance is simply the sum of the resistances of all individual components. Returning to our hallway analogy, where each checkpoint represents a component in the circuit, think of resistance as the challenge or effort required to pass through each checkpoint. At every checkpoint, people, representing electrons, have to climb some steps or squeeze through a narrow gate, which slows them down. These steps or narrow gates symbolize the resistance in each component. Since the people have to go through each checkpoint one after the other, they encounter every obstacle along the way. The total effort they need to get through the entire hallway is the sum of all the individual efforts required at each checkpoint. Similarly, in a series circuit, the total resistance is the sum of the resistances of all the components. You may hear the term equivalent resistance being used instead of total resistance. The concept of equivalent resistance is used to simplify understanding and calculations in a series circuit. It is like imagining that instead of multiple checkpoints in the hallway, you replace them all with one big checkpoint that has the same total number of steps or narrow gates as all the original checkpoints combined. In circuit terms, the equivalent resistance is asking yourself, if I were to replace all the current resistors with a single resistor, what would its resistance need to be for it to have the same effect on the current? This concept is helpful because it allows us to calculate the overall impact on the current with just one value, making it easier to analyze and design circuits. Consider a series circuit with two resistors. The first resistor has a resistance of 3 ohms, and the second resistor has a resistance of 5 ohms. The total resistance in the circuit would be the sum of these two resistances, which is 8 ohms. This means that if you were to remove the two resistors and replace with an 8 ohm resistor, the current wouldn't change. In today's lesson, we delved into the variations in current potential difference and resistance in a series circuit. We began by revisiting what a series circuit is, emphasizing its single-path structure for current flow. We learned that the current in a series circuit remains consistent throughout all components, as there's only one path for electrons to travel. We then explored how the voltage is divided among components, with each component using a specific amount of the total energy supplied by the source. Next, we discussed that the total resistance in a series circuit is the sum of individual resistances, which affects the overall current and voltage drop across each component.